Okay, this is the Unit 3 exam review, and I will be working through select problems on it. So, in number 1, they're asking us to find the extrema of the function on the given closed interval. So, notice that we are given an interval and we're given a function. So, our goal here is to take the derivative. Then we need to set the derivative equal to 0 or find where the derivative does not exist. That results in what we call our critical values. Then you take those critical values and the endpoints of the interval, okay, and you plug those into the original equation to yield some outputs. These outputs are y values. So when they are asking for the extrema, that's the absolute max and the absolute min, they're asking that is a y value. So they're saying at what x value does the maximum y value occur or the minimum. So in this first example, the absolute maximum was 0 because if you'll notice all of these were negative, so the highest one of those would be 0. So the absolute max was at 0, 0, and the absolute minimum was going to be at the x value of 4 and the y value of negative 32. So very similarly, we can do that with some trig as well. So for this first one, I'm just going to take the derivative and set it equal to 0. So here, the derivative of sine is cos, so this is just going to be 2 cosine of x minus 1, okay? And I need to set that equal to 0 or find where it doesn't exist. I do not need to worry about where that doesn't exist because cosines, it's not divided by 0 or anything like that. So basically I set that equal to 0. So I end up with cosine of x equals positive a half. And what we're saying there is where on your unit circle does cosine equal 1/2? Well, cosine's positive in quadrants 1 and 4, and that's going to be my pi over 3's. So cosine is a half at pi over 3, and also positive a half at 5 pi over 3 down in quadrant 4. And just like before, we're going to take the critical values there, and we're going to plug them into the original. And also we need to make sure that we plug in our endpoints. So we just take all these. Sometimes I do my endpoints first just so that I don't forget them. But I'm doing them second here. Okay, so go ahead and plug those in. And remember, when you're plugging these in, you're going to be plugging them into the original. And when I plug in 0, I get 0. When you plug in 2 pi, I get negative 2 pi. When I plug in 5 pi over 3, ooh, that's going to be a nasty one. That'll be like negative radical 3 minus 5 pi over 3. Yuck. And then if I plug in pi over 3, that'll be radical 3 minus pi over 3. Okay? So, you can kind of get an idea of what those are. If you needed to use your calculator to kind of get an idea of what those are, you can. But the maximum is actually going to be this right here, because it'll still be positive. Like, obviously, and then the minimum, if we have this, a negative minus another, 15 over 3 minus 5, that'll actually be our minimum. So we can say that there is an absolute max, okay, at pi over 3, comma, radical 3 minus pi over 3, and I'm not even going to change that to a decimal, and at 5 pi over 3, and the y value would be negative radical 3 minus 5 pi over 3. Okay, and that's how you do that. Now, in example number 2, they're asking to identify the open intervals on which the function is increasing, decreasing, okay? So that's classic first derivative test, and what we want to do here is use the first derivative test, and then we're going to set the derivative equal to 0, find where the derivative does not exist, and then we'll have to do a sign chart. Remember, a sign chart is going to be able to tell you when you plug in, you care if the derivative is positive or negative, and then that's going to tell you the behavior about the original function. So in this example, I'm going to take the derivative. Okay, and this is going to be a chain rule, so you bring the 3 out, you recopy this, you decrease the exponent by 1, and then you multiply by the derivative of the inside. The derivative of the inside here is just a 1 though, so that makes it a little bit easier. And I set this thing equal to 0. So if I set that equal to 0, okay, you could divide both sides by 3, and you'll just get this. Then you square root both sides, and you just get this, because the square root is 0, 0. So after all that work, you end up with x equals a negative 1. Okay? So that negative 1, again, is called your critical value or your critical number. And from there, we are going to use a sign chart and put it on the sign chart. Okay, so I only have one critical value, so I'm just going to stick it right there. And remember, I plug into the derivative, and I only care if the derivative is positive or negative, and that's going to tell me the behavior of the function. So when I plug in a number to the left of negative 1, so I don't know, like a negative 2, into the derivative of negative 2 plus 1 is negative 1, squared is a positive 1, times 3 is still positive, so I get a positive over here. And then I plug in a number to the right of it, so 0 is probably the easiest thing. If I plug in a 0 there, square it, that's positive times a positive, so I still get a positive over here. And again, it's not uncommon for that to happen. It usually alternates, but it doesn't have to. So in this case, that tells me that the original function is increasing the entire time. If you kind of think back to what your parent cubic graph looks like, right, that makes sense. This is just your cubic shifted to the left by 1, so you should even be able to kind of get that it is increasing from left to right the entire time. So this is increasing over the interval, right, so f of x is increasing on the interval negative infinity to negative 1, union negative 1 to infinity. Alright, and that is the end of page 1. Okay, for number 4, we are asked to find the critical numbers, and then we're also asked to find where it's increasing or decreasing, and also finding the extrema. So the first thing you're going to want to do here to find the critical numbers is you're going to take the derivative and set it equal to 0. So here, the derivative, h prime of t, so 4 times 1/4 is 1, so that'll just be t cubed minus 8. And then you set that derivative equal to 0, so that ends up with t cubed equals 8, and that tells me that t equals 2. So then that brings me right down to where it says find the intervals where it's increasing or decreasing. So that's asking me to do a sign chart. So I take that critical value of 2, I put it on the sign chart, and I'm plugging into the derivative. So when I take 2 and I plug it into the derivative, that's going to be, take a number to the left of 2, so like a 1. 1 cubed is 1 minus 8, that's going to be a big old negative number there. Then I plug in a number to the right of 2 on the sign chart, so like a 3. 3 cubed is 27 minus 8, that's still going to be positive. What does that tell me about the original h? It tells me that it was decreasing until it hit 2, and then it started increasing. So I can say that h of t is increasing on the interval 2 to infinity, and is decreasing on the interval negative infinity to 2. To find all the extrema, express your answer as an ordered pair. So this is just kind of breaking up all the steps here. So to find the extrema, that's finding a max or min. So looking at this sign chart, if you are decreasing and then increasing, well, that tells you here that this 2 is a minimum. Okay, if you were increasing then decreasing, you'd get a max, but this one's a minimum. That's the only critical value I have, so express it as an ordered pair. Oh, so I need to say that there is a relative minimum at, and it's 2 comma, it wants it as a point, so that means I need to go and get that other value. Well, how do you get that? You're going to take this 2, and you're going to plug it back into the original, okay? So when you plug that 2 into the original, 2 to the 4th power is 16 times 1/4 is going to be 4. So I've got 4 minus 16 there, because if I plug in a 2 right here, so that'll give me a negative 12 as my y value there. And I'll just make a note here that there is no relative maximum on this problem. Alright, perfect, and that's how you do number 4. Okay, for number 5, we have f of x equals cosine of x minus sine x, and we're basically just trying to do the same thing, but this one has trig. So again, to find the critical values, your goal is to take the derivative, set it equal to 0, right? And then we're going to use a sign chart to figure out if they are maxes or mins. So here, the derivative of cosine is negative sine x. The derivative of negative sine is going to be negative cos. So I take that and I set it equal to 0. And this is one where people get a little bit confused, because when they set it equal to 0, they're like, well, I can move one of them over, but where in the world does cosine equal negative sine, or where does negative sine equal cosine? So for that, I'd basically like to kind of point out this unit circle here, and we're looking for where cosine and sine are the same. Well, they're the same at all your pi over 4s, right? They're both radical 2 over 2, but I want to know where one of them is the opposite of the other. So that would only be, see how this one's negative and this one's positive, and then down here this one's positive and this one's negative? So those are actually the angle measures that I want to work with for here. So this is going to give me the x value of 3 pi over 4, and then down in quadrant 4 it was 7 pi over 4. So those are your critical values. And then to figure out where the original is increasing or decreasing, I'm going to, notice that it's a trig function, so I would give it an interval. So when I do my sign chart, instead of having like the arrows, I'm actually going to have them stopped there, and I'm going to go from 0 to 2 pi because that was my given interval. And then I put these critical values on there, and they go on there like this. And again, I'm plugging into the derivative, so I indicate that by putting the derivative up there, and it's going to tell me the behavior about f of x. So to do this, I plug in a number between 0 and 3 pi over 4. So an example might be something like pi over 4, right? So when you plug in pi over 4 into the derivative, right? So if you plug in pi over 4 into the derivative there, the sine, but you're going to have to negate it, and then you have minus the cosine of pi over 4, which is radical 2 over 2, negative radical 2 over 2. So this one's actually going to be negative there. When you plug in something between, a good example of something between there would be something like pi. So when you plug in a pi, the sine of pi is 0, so negative 0, and then the cosine there is a negative 1, so it'll be minus a negative turns to a positive there. And then you could plug in something over here, I don't know, 11 pi over 6 would work. Anything to the right there. And that's going to be negative when you plug in there. So that tells me that the original is decreasing, then increasing, then decreasing. So if you're decreasing and then increasing, that means that this guy here is going to be a minimum. And if you're increasing then decreasing, that means this one here is going to be a maximum. Sorry, that A got a little messed up there. So that's a maximum there. And it says identify the extrema, and what they want it as an ordered pair. So I can say that I have a relative max at, it'll be 7 pi over 4 comma something. How do you get that something? You actually have to go back and plug this 7 pi over 4 into the original. So when you plug that 7 pi over 4 into the original, you get radical 2. And then you have a relative minimum at 3 pi over 4, and you take that 3 pi over 4, plug it back into the original, and when you do that, you'll get a negative radical 2. Oh, up here I forgot to actually make my conclusion. So I can say here that f is increasing on the interval 0 to 3 pi over 4, and then, oh, whoops, that's decreasing. It's decreasing on the interval 0 to 3 pi over 4, and then union, and then, oh, am I going to be able to fit it in there? 7 pi over 4 to 2 pi. And I could say that it is increasing on the interval 3 pi over 4 all the way to 7 pi over 4. Okay, so there's my conclusion for number 5. Okay, number 6 we're going to go through really quickly. You're going to take the derivative, and then you're going to actually take the second derivative, because for the points of inflection, it's not asking me to conclude anything about increasing or decreasing. So I'm going to take the first derivative, and that's going to be 3 minus 15x squared. And then I go straight to the second derivative, which is just going to be a negative 30x. Well, negative 30x, I set that equal to 0, and you end up with x equals 0, right? So that x equals 0 is a possible point of inflection, so I'm going to do my sign chart real quick. Okay, so when you put 0 on your sign chart there, again, you're plugging into the derivative. You get a positive for a number to the left of 0, a negative for a number to the right of 0, and these are your final conclusions. Okay, this is still the Unit 3. This is going to be Part 2. It will be the second half of the review, so pages 4 and 5. If I were you, I would definitely circle number 7 because there are 2 of them like it, I believe, on the test, so that's a good place to start. And remember, in this one it says find the value of c satisfied by the mean value theorem for that function there over a given interval. Remember, the mean value theorem just basically says that the slope of a line through there is going to be equal to the derivative. At some point on there, they're going to be the same. So this is the one where you're going to need to take the derivative of this, and then you're also going to have to use that average rate of change formula from pre-calculus. So a couple things I'm going to do first. First, I'm going to rewrite my f of x, and instead of a square root, I'm going to write it as 2 x to the 1/2 power. And then I'm going to remind myself of that average rate of change formula from pre-calculus that says f of b minus f of a over b minus a is going to give us the slope. Okay, so now that I have those written down, I can kind of go ahead and take my derivative here. So I take the derivative, and when I take the derivative, 1/2 times 2 is 1. So I'm going to get x to the negative 1/2 when you subtract an exponent, okay? And then that, just so we know, remember, a negative exponent means you're in the wrong spot of the fraction, so I would rewrite this as this over square root of x, okay? And now I'm going to use this average rate of change formula from pre-cal, keeping in mind that my interval over here is my a and my b. So really I need to plug in, so let's see, that'll be f of 9 minus f of 0 all over 9 minus 0. And let's see, so if I plug in 9 into the original there, 9 squared root of that is 3 times 2. Okay, so 3 times 2 is 6. And then minus, if I plug in a 0, that'll just give me 0. Divided by 9. So really, I'm asking myself to reduce 6/9. So when I reduce that, I get 2/3. Okay, so really the mean value theorem is saying that I want to take this derivative and set it equal to the average rate of change, because they're saying that somewhere on that graph, the average rate of change equals the derivative. Remember, the average rate of change is how we found slope in pre-calculus. So we're just setting those two things equal and solving for x. So I'm really just saying 1 over square root of x equals 2/3. To solve this, all you need to do is cross multiply. So you have 2 square root of x equals 3. Divide both sides by 2, and you get square root of x equals 3 over 2. And then you square both sides, so you end up with x equals this squared, right? Quantity squared. And remember, when you're squaring this, you have to square the numerator and the denominator. So my final answer is going to be 9/4. And that would be the value of c. And again, I would definitely make sure you know how to do something like that, because that one for sure shows up on the test. Okay. The optimization problems here, you could have over here solved for y instead of x. Either way, you should end up with the same answer there. Make sure you know how to do this one like 8 and 9. Those are definitely both on your test as well. Okay, so moving on to the calculator section. So it says the derivative is given by this here. For which values of x, if any, does f have a relative maximum? So here they're asking you to find the relationship between the derivative and the original. So if you have your calculator, okay, how you would type this in over here. So turn this on. Oh, I already got it in there. So y equals, okay, you're going to hit your y equals and you're just going to type it in. So you just type in x squared, and then in this one it is minus, right, ln, and then it's 5x, close it. So when you hit graph, this is what you'll see. Oh, you won't probably see that. Let me change it, because the original window that you are going to see is going to look more like this. Okay, so remember, when you are given the graph of the derivative, you really care about where the derivative is positive and where the derivative is negative. My suggestion here would be to make a sign chart. And if you want to zoom in, just hit zoom, and then it's choice 2. You can kind of zoom in there, and you have to hit enter for the calculator to actually do it. Okay, so I'm just going to scooch this up. Okay, so here's what I'm looking at. Again, this is my suggestion, is to do a sign chart. You don't have to. But I think it kind of makes it easier to see, and you're like, well, if I'm worried about where my derivative, right, goes from positive to negative, that means I want to know this part here where it's positive, and then this part where it's negative, and then this part where it's positive. So really I'm concerned about those two things right there. Well, those are called the zeros, and to find those on your calculator, okay, you hit second, then the trace key, you find the zeros, so you select 2. It asks you to go to the left of it, so you kind of go near the 0 and hit enter. Then you arrow a little to the other side of where it crosses the x-axis there and hit enter twice. So when you do that, it'll spit back that first critical value. So that's going to be at 0.209. And then it looks like there's another spot, so you hit second, trace, zeros again. So we're going to go arrow over till I'm just near it, and I hit enter. Then I arrow to the other side of it, and I hit enter twice. And then this time, it tells me I am at 1.393. Okay, so looking at the graph, I don't even need to plug in anything. I knew that it was positive to the left of that, it was negative in between, and it was positive after. Well, what does that tell me about the original? Remember, that's what the beauty of the sign chart is it gives you the relationship between the derivative and the original. So that means my original was increasing, then the original was decreasing, and then it was increasing again. Well, if something goes from increasing to decreasing, that means you have a maximum there. And then if it goes from decreasing to increasing, that means you've got a relative minimum there. And then I need to make sure I answer the full question. Here it says, does it have a relative max? Yes, it has a relative max. So I would say relative max at x equals 0.209. And again, since you have your calculator, you could go back and plug this into the original to get the actual point there, but, oh, no, you don't even have the original, so you wouldn't be able to do that because you're only given the graph of the derivative, but it does have a max there. Okay, so that is how you would tackle something like number 10. This is Unit 3. This will be the page 5, and primarily using the calculator. Okay, so in number 11, they are asking us to find the intervals over which f is increasing or decreasing. Now, there's kind of 2 ways that you can do this. I'll do it kind of the calculus way first, and then both of them are going to involve the calculator, but there's kind of 2 ways where you can do it. So when you're trying to find intervals of increasing and decreasing, you should be thinking that you want to take the derivative, okay? So when you take the derivative, careful, that's a chain rule. The derivative of cosine is negative sine, so it's going to be negative sine of 3x times the derivative of the inside, which is 3. So it'll be negative 3 sine 3x. And then the derivative of this part over here is just a negative x. Okay? So my goal is to take that derivative and find where it equals 0 or where it doesn't exist. I don't need to worry about this one not existing. So I'm just going to take this and 3x, and I'll set it equal to 0. Well, that's where my calculator is going to come in handy, okay? So to figure out where that equals 0, the easiest way to do that is to turn your calculator on, right? Hit y equals, and we're going to type that in. So negative 3 sine 3x. Notice my calculator is in radian mode, and it was a minus x. Perfect. So I would recommend hitting zoom and then maybe trig here. Let's see what that does. There we go. Oh, and keep in mind here that I'm only looking at the interval of -1 to 3, so it would probably be a good idea to adjust that window so that I'm not getting all confused with all this stuff. So when I go to my window, if my interval is -1, I like to do like -1.1, and then for my x max, it'll be 3.1, just so I see a little bit on either side, and then I can graph it. And that'll kind of just tighten up that window so I really can see what I'm looking for. Now, again, I'm trying to figure out where this thing equals 0. So to do that, you're going to be hitting the second key and then the trace, and then you're going to find where it hits 0. Well, the first one's pretty obvious there. You can see that it crosses right at 0, but you can still, if you wanted to, right, figure that out using that. I won't waste the time, but yeah, so it crosses at 0, and it's also going to cross over here. So left, I hit enter, I go to the right of it, and I hit enter twice. This will give me my second critical value there. So again, this yields that x equals 0 and 1.182. And then to get the second, or the last one there, and then I'm going to go to the left of it, hit enter, go to the right of it, hit enter twice, and that last one was 1.870. So those are going to be my 3 critical values that I am then going to put on a sign chart. Okay, so we're going to take this information, and I like to put it in a sign chart. Remember, a sign chart tells you the relationship between the derivative and the original. So here, the derivative, you could see that to the left of 0 it was positive, and then between 0 and down there it was negative. And then up here again it was positive, and then it went to negative. So that tells you that the original was increasing, then decreasing, then increasing, then decreasing. And that's what it's asking me for. So I can conclude that we were increasing on the original was increasing from negative infinity to 0, union from 1.182 approximately, and that was until 1.870, and it was decreasing on the interval 0 to 1.182, and then decreasing again from 1.870 to infinity. Okay? Now, the alternate solution for this, so if this makes sense to you, I would say just kind of skip the next minute or so. But the alternate way that you could have solved this is because you were given your calculator right from the beginning, you could have, instead of even taking the derivative and risking making a mistake, you could have just typed in the original into the y equals here, and I'm going to say 0.5x squared, okay? And you could have graphed that. Now, the difference here is that you have to look for the relationship. We're looking for the intervals over which it's increasing or decreasing. So if you were looking at just this graph, you would be looking for the maximums and minimum points. So you would be concerned with this right here and this peak right there. To find those, you'd hit second, calc. You'd go to choice 3, minimum, and then you'd go a little to the left and a little to the right of that minimum to find it. Notice that it gives you that same 1.18 that we got previously, and to find the other one you could do second, calc, maximum this time, and I want to go to this peak here, hit enter, and then go to the other side of the peak and hit enter. And again, it gives us that 1.87 number. And again, you could tell right away that at x equals 0, it also has a maximum there. So that's the other way, but I actually prefer the sign chart, and that's what I would recommend that you do it. Okay? Okay, so now, number 12 is the last calculator question, the last one that I'm going to be working through. So it says, for this function, find the intervals where you're concave up or down. So when I see concave up or down, that leads me to believe I'm going to need to use my second derivative test. Okay, so I'm going to take the second derivative. So the first derivative, it's going to be negative 4x cubed plus 3x squared minus 1. And then over here, what am I going to have to do for this? Well, the derivative of e to the x means you recopy it, and then you multiply it by the derivative of the exponent. So let's see. The derivative of the exponent is going to be a negative 2, and I recopy it exactly as I see it. So there's the first derivative. Now, the second derivative. So now I'm just taking the derivative of this line here. This times this, that'll be negative 12x squared plus 6x. This negative 1 completely goes away. And again, to take the derivative of e to the junk, you recopy it, right? And then you multiply by the derivative of the junk. So if I recopied this, but then multiplied it by a negative 2, it would end up being a positive 4e to the negative 2x. So there's my second derivative. And my goal here is to set that equal to 0. So then I'm going to use my calculator. So I set this equal to 0, and to do that you just type it in to the y equals of your calculator, and then we're going to find the zeros just like we did in the last problem. So let's see here. So I clear any junk out of there, and I'm typing this in. So negative 12x squared plus 6x plus 4 second e raised to the negative 2x. Okay, I always just kind of look at it at the end to make sure that that's how I want it. And I'm going to hit zoom 6 this time because my window was all messed up from before. So I want to get back to a normal window. And it's just going to take a second to graph it there. And so this only has one critical value because it only crosses the x-axis once. If you need to zoom in, you can. I don't think I need to. So I'm just going to hit second calc. And then I go to the left and to the right of it. And let's see, that's going to be at 0.643 when I round. So I'm just going to note that. So this occurs at x is approximately 0.643. And I can do a sign chart there. Okay, so at 0.643. Well, what can you tell me about it? Well, before it was positive, right? To the left of that number, it's positive. Below that number, it's negative. So that means that the original must have been concave up, right? Because we're talking about my second derivative in the relationship to the function. And after that, it was concave down. So I can conclude that it is concave up on the interval negative infinity all the way to that 0.643 number. And I can also conclude that it is concave down on the interval 0.643 to infinity. Like that. So, because it did switch concavity, I can conclude that there is a POI at that 0.643. Now, how do I get the y value for that point of inflection? What I would do is go back to your y equals and type in the original, that negative x raised to the 4th plus x raised to the 3rd minus x plus e to the negative 2x. Oh, that's all messed up. Well, I would type that into the original, type that into your y equals, and then hit second calc value, and then just type in that 0.643 number. If you do that, you should end up with negative 0.272 as your point of inflection. Okay? Alright, I'm just going to quickly walk through that last problem. Okay? So here's the last problem there. Whenever you're given the graph, you need to make sure that you're paying attention to what they're giving you. In this example, they're giving you the derivative. So my suggestion is to turn this graph into a sign chart. Remember, we care about when the derivative is positive or negative. So I was saying that it's positive till about negative 4.5. Then it's negative until you get to 0, when it goes to positive from 0 to 2. And then this didn't quite cross at 5. I think I intended it to cross at 5. So I just kind of said 5-ish. Okay? So that tells me that the original was increasing, decreasing, increasing, decreasing, increasing. Well, that helps me conclude that there must be a max here, and I'm in there, a max here, and then I'm in there. Okay? Remember, a point of inflection only occurs when you switch concavity, aka when your derivative switches from increasing to decreasing or decreasing to increasing. Okay? So where does that happen? So you have to look back at the original graph. So this graph is decreasing here, then it starts increasing, which makes this a point of inflection. It's increasing, then decreasing, which makes that another point of inflection. And then it's decreasing to increasing, so there. Those are the values of negative 3, 1, and 4, which is where I got those from there. Okay? So good luck, and on your test for Unit 3.